I thought a great deal about how we should spend the rest of this section, what material we should cover. And I finally decided that it was a good idea to get a really firm understanding of linear systems. And that may seem kind of strange because you say, well, we have computers that can compute all these things, they can solve linear systems like that. Why do I need to understand it? And mostly it's because of the fact that an understanding of linear systems is not only important because they're the most important, they're the most commonly occurring sort of operation that we do in applied math, but they're also very important because when we're doing statistical models, linear systems arise constantly. And without a good understanding of linear systems, you don't really understand what you're doing. Okay, I've had some very smart students, graduate students from good universities, even ask me incredibly stupid questions. And it's not because they're stupid, it's just because they never learned linear regression properly. They learned it as a bunch of formulas, which is the wrong way to learn it. So we want to go into the nuts and bolts of what the solutions are like. And here's the basic idea. So we proved before that a linear system can have 0, 1, or an infinite number of solutions. In the case of exactly one solution, we've pretty much beaten to death. We know exactly when we're going to get one solution. We had those 6 equivalent conditions, right? And we also know exactly what the solution is going to look like. When there's exactly one solution, we can always invert the matrix and we get our solution. But there are two cases that we haven't considered. And the first is the case where there are no solutions. And the second is the case where we have an infinite number of solutions. And we kind of have an intuitive feel for when we're going to get no solutions. If we have, for example, some augmented matrix, and in the row echelon form, the last row of A is 0, but the corresponding element for B is not 0, notice what this tells us, which of course is not satisfied for any X, Y, or Z, right? So basically, when the last row of a row echelon form matrix is 0, but its right-hand side is non-zero, we're going to have no solutions. Okay, and this occurs often when we have more equations and unknowns. This is typically where we see this occur. Now, what's interesting is we do solve these equations in a sense. These systems occur very commonly in any sort of linear statistical model, and regression just happens to be one model, but there's a whole lot of them. How do we do that? Well, we compromise. We find the vector x such that ax is the closest to b that it can possibly be. And that's what we call a least squares solution. Okay? Now we have this other problem that we can have an infinite number of solutions. And we'd like to know also, well, when is that going to occur? And we already showed that for a homogeneous system, when we have more rows than columns, we're going to get an infinite number of solutions. But what if we have a non-homogeneous system? You know, the right-hand side vector b is not equal to the 0 vector. When are we get an infinite number of solutions then? And we'd also like to know a little bit about what the structure of the solution is going to look like too. Okay? And so we're going to try to tackle all of these problems today. Before we do this, I want to first of all talk about a few terms that we're going to need. We're going to consider some matrix A, which is an m by n real matrix. And we're going to define the row space of A, which I'm going to denote by row A, as the span of the row vectors of A. So it's the set of all linear combinations of the row vectors of A. We're going to have a similar space for the columns of A. We're going to call it the column space of A, denoted by col A. And that's going to be the span of the column vectors of A. We've already talked about the kernel, and actually that should be AX is equal to the 0 vector. Sorry. I don't know why that came out B. Okay. And we're also going to want to, every once in a while, talk about the row space, the column space, and the kernel of A transpose. And one of the things that you know automatically is that since the rows of A transpose are the columns of A, the row space of A transpose is a column space of A, and conversely, the column space of A transpose should be the row space of A. And sometimes I'm going to use a bit of notation. I'm going to use U to represent the row echelon form of A. The reason why we use U is because when we have a square matrix, the row echelon form of A is generally an upper triangular matrix. So that capital U is going to stand for upper triangular matrix, okay? All right, so we want to look at the case of infinite number of solutions first. And there's kind of this scheme that we're going to follow. The first is we're going to show that we get an infinite number of solutions when the number of linearly independent rows of A is less than the number of columns of A. All right. And next we're going to show that the solutions, when we have an infinite number of solutions, are given in terms of linear combinations of the vectors that are the basis vectors for the kernel of A. And the last result we want to show is we want to show that when we write the parametric form of the general solution, the number of parameters are equal to the number of basis vectors in the kernel of A. And if this doesn't make any sense right now, that's okay. We're going to explain this as we go along. So I want to show the first result, which is that we get an infinite number of solutions when the number of linearly independent rows of A is less than the number of columns of A. And here's how the flow of the argument is going to go. First, we're going to show that AX equal B has an infinite number of solutions if and only if the kernel of A is not the zero vector. Then we're going to show that since the kernel of A is a subspace, if it has more vectors than the zero vectors, the dimension has to be positive. And from that, we're going to prove a very important theorem. This is called the rank plus nullity theorem. It's going to say that the number of linearly independent rows of A plus the dimension of the kernel of A, excuse me, I'm sorry, is equal to the number of columns. Okay, this is very important. And this is a fundamental theorem of linear algebra. And so from that, we're going to be able to get our result. We're going to be able to conclude that we have an infinite number of solutions if and only if the dimension of the kernel is greater than 0, which is true if and only if n minus the number of linearly independent rows is greater than 0, which is true if and only if the number of linearly independent rows is less than the number of columns. So that's kind of the logic that we're going to use here. And we're going to prove all of these things now. Okay, so let's first of all prove that AX equal to B has an infinite number of solutions if and only if the kernel is not just equal to the zero vector and AX equal to B has at least one solution. Okay, so let's go ahead and do the forward proof, and I'm going to let you do the forward proof. Go ahead and suppose that AX equal to B has an infinite number of solutions. And basically, if we have an infinite number of solutions, we have at least one solution. So all we have to do is prove that the kernel doesn't consist of the zero vector. And we actually did this proof earlier on in one of the earlier lessons. So, but see if you can prove it now for yourself. And we're going to do the backwards proof also. We're going to suppose that the kernel is not just the zero vector and that we have some solution, and we want to show as a consequence the solution of AX equal to B is going to be infinite in number. And I'm going to leave these again as exercises for you to do. So let's go to the second result. So we want to show that if the kernel of A is not equal to the zero vector, this implies that the dimension of the kernel of A has to be positive. Okay, so let's start off. Let's suppose that A is an m by n matrix, and the kernel of A does not just consist of the zero vector. We know the zero vector is in there, but there's something else. Therefore, we know there exists an element of the kernel of A that's not equal to 0. And we know that a single vector is a linearly independent vector. So X is a linearly independent collection of vectors in the kernel of A. Now, remember what we talked about in the last video. We said the kernel of A is a subspace. So we have a linearly independent vector in that subspace. So we know that the number of vectors that span a subspace is the number of basis vectors. That's going to be the dimension. So the dimension of the subspace is always going to be greater than or equal to the number of vectors that are linearly independent in that subspace. Because again, remember, we can never have more linearly independent vectors than we can have basis vectors. So the dimension is the number of basis vectors. So this always has to be greater than or equal to any linearly independent set. So since we have one linearly independent vector, we know that the dimension of the kernel has to be, and technically I should have greater than or equal to 1. Let me change that. Okay. Because it could be 1. And sometimes we call the dimension of the kernel of A the nullity of A. I may say that once in a while, but it's a very commonly used term. Okay, now we got to prove the last step. So this is the tricky part. We have to prove that the dimension of the kernel plus the dimension of the row space is n. Okay, let's start with what we know. We know that both of these are subspaces of Rn. Okay. Now, if we can show that the kernel of A is the orthogonal complement of the row space, then we know from that previous theorem that the dimensions of orthogonal subspaces add to the dimension of the space they're in. And these are both in Rn. Now, to show the kernel of A is orthogonal to the orthogonal complement of the row space of A, we have to show two things, right? First, we need to show that every vector in the kernel of A is orthogonal to every vector in the row space of A. And then we need to show that their intersection is only the zero vector. And that's sufficient. So let's go ahead and do that. So the first step, what we're going to do is we're going to construct a basis for the row space of A. So I'm going to let there be m rows in A. I'm going to call the first row row 1, literally, on up to row m. And I'm going to construct a list. L1 is going to be the first non-zero row of A. Okay? So I1 is the index for the first non-zero row of A. And then I'm going to tack onto it row I sub 2, where row I sub 2 is the first row after row I sub 1 that's not in its span. Okay, so I'm building up a linearly independent set. And I'm going to keep doing this. And eventually, I only have m rows. I have to exhaust, right, this process. I'm going to get to the point where I have r linearly independent rows, and they're going to form a basis for the row space. Okay. Every other vector can be written as a linear combination of them. Okay. So now we want to show that every element in the kernel of A is perpendicular to every vector in the row space of A. But that's not hard, because we know that if x is in the kernel of A, ax is equal to 0. And think about it. How did we get the ith element of ax? We take the dot product of the ith row of A with x. So that means that every row of A, its inner product with x is 0. Therefore, it's true for the ones that are in our basis set. These are just specific rows. So now we know that every basis vector for the row space is perpendicular to any vector in the kernel. And you can show from that, and I'll let you show that, this implies that x is orthogonal to every vector in the row space. Okay, if you can show that a vector is orthogonal to all the basis vectors for a subspace, it's orthogonal to that every vector in that subspace. I want you to show that. Okay. And the last thing you need to show is that the intersection of these two subspaces is a zero vector. And I'm going to leave that as an exercise for you to prove. Okay. And that's it for the case of well, that's it for the first part. So we've basically done up to here right now. Okay. And we're going to get these last two topics in the next video.